Hello students, I am Dr. Himani Sharma from the Department of Physics, University. So we are starting with our second module of the paper Analog Systems and Applications. In the first module, we have studied about the PN junction diode and about the semiconductors and various concepts of semiconductors. What are semiconductors? What is their mobility? What is their resistivity? How the PN junction is formed? What is the concept of barrier? Also, in our last module, I gave you the quiz. Hopefully, you have gone through the quiz and solved it. Now, in our second module, we are going to study about the PN junction, their VI characteristics, and their various applications. So, if we talk about PN junction, it's basically a crystal diode in which the current conduction takes place only in one direction. So these PN junctions, they have variety of applications. For example, they are being used as rectifiers. Rectifiers are half-wave rectifiers, full-wave rectifiers. They are also being used in solar cell applications, they are also used as light emitting diodes. And apart from that, their properties also lie when they show the characteristics of the reverse biasing, that is the photodiode. So all these applications we are going to study in this particular module, and in the end I will provide you a quiz. Hopefully after having the concepts or understanding of the concepts of the second modules of PN junction and their application, you are able to solve that quiz. So all the best with that. So we are going to study the details about that particular module. So this is the description of the module. The paper name is Analog System and Applications, and the title is PN junction diode and their applications. So contents of the module are as such: introduction to diode, VI characteristics, diode as rectifiers, half-wave rectifier, full-wave rectifier, and their application, particularly as light-emitting diode. After having the idea of this contents of the module, the learning outcomes will be diode and their characteristics, applications of diode, rectifiers, ripple factor and their efficiency, light emitting diode, etc. So starting with the PN junction diode is a two-terminal electronic component that conducts current primarily in one direction. So it's basically a unipolar device. It has a low resistance to current in one direction and high resistance in the other. The primary purpose of a diode is to allow electric current in one direction, while blocking it in the opposite direction, which is the reverse direction. So this is the property of a PN junction diode, that it conducts current only in one direction. So the principle of diode is basically is a piece, or a crystal diode is a piece of semiconductor material with a PN junction. The P side contains an excess of positive charge carriers, while the N side contains an excess of negative charge carriers. When a positive voltage is applied to the P side and the N side is connected to the negative terminal, the diode allows the current to flow. Conversely, if the polarity is reserved, it blocks the flow of current. So you may see the picture of the PN junction diode, which is being shown in this particular figure. So this is the PN junction diode. This is the P side, which is being represented as an arrowhead, and the line, which is the N side. So P is the positively connected for the forward biasing, and N is negatively charged. So this arrow basically points in the direction of conventional current, which flows from positive to negative side. The actual structure of a diode, it consists of a semiconductor crystal that forms the PN junction. The two sides of the junction have different doping profiles, with P side doped with materials that produce a surplus of holes, and the N side doped to produce a surplus of electron. Hopefully you have the idea what is the PN junction diode. So this is the characteristic and the types. So VI characteristic, this particular figure shows the VI characteristics of a diode. So as I said, when you connect the P side of a semiconductor to the positive terminal of the battery and N side to the negative terminal of the battery. So and when we measure the current to the applied voltage, this kind of curve is being shown. So this side corresponds to the forward side and this side corresponds to the reverse side. So the current characteristics of a diode is being shown here, which is non-linear, and in the forward direction, as the voltage is being increased, the current starts to increase basically. Initially, what happens when you apply the voltage, you see uh, a small rise in the current basically. So this small rises correspond this small rises basically corresponds to the barrier that we have studied in the last module. So a small barrier is there, and when the voltage is being applied, so that voltage overcomes that barrier, so there will be a sharp rise in the current. So initially a very small rise there after increasing the voltage, then when this barrier is being overcome, then there will be the sharp rise in the current, which is the characteristics of the forward biasing. So and when we see in the reverse biasing, as you may see here, the current is being increased in the reverse direction corresponding to the applied voltage, and up to a certain value, when the a point reaches, then there is a sudden uh, rise in the current in the reverse direction, and we call that rise as a breakdown voltage. Talking about the forward biasing, there is a point that comes where you have a sharp rise in the current. So that particular point is known as the knee voltage, which occurs in the forward biasing. And in the reverse biasing, we have a breakdown voltage, which shows the sharp rise in the current in the reverse side. So when the P side of the diode is connected to the positive terminal of the battery and the N side is connected to the negative terminal, the diode is said to be forward biased. As the forward voltage reaches a certain threshold, which is typically zero point 0.6 volt to 0.7 volt for silicon diode, the diode starts to conduct and the current increases exponentially. So that particular voltage corresponds to the knee voltage. The voltage at which the diode begins significant conduction is called the knee or the cut-in voltage. So this particular point, if I show here with the dotted line, but this particular point corresponds to the knee voltage. So here you'll be having the knee voltage. If I draw here this particular point, this is known as the knee voltage, which shows the sharp rise in the current. All of a sudden there is a sharp rise. I think I'm, yeah, so this particular point, this is known as the knee voltage to this particular point here. So this is the knee voltage, and in the reverse side we have a breakdown voltage. If we talk about the reverse bias region, when the P side of the diode is connected to the negative terminal of the battery and the N side is connected to the positive terminal of the battery, the diode is said to be reverse bias. We have already discussed. In this region, only a negligible or the small amount of current flows, which is the current because of the minority carriers. And the current in the reverse bias is very small, which is in the range of microamperes, and in case of forward bias the current is in the range of milliamperes. Reverse voltage increases, the current remains nearly constant up to a certain point, and after that you'll be having a sharp rise in the reverse direction, to which we call as the breakdown voltage, that particular voltage at which you'll be having the sharp rise in the current. Hopefully you you had an understanding of the forward and reverse biasing of a PN junction diode. Then there are various applications of PN junction, because it's a two-terminal device and it has the quality that it conducts current only in one direction, which is that's why it's known as a unilateral device. It means it could, when you apply the biasing to that, it would be conducting in one direction and other side it will be blocking. So because of this particular application, this is being used in various applications. So one of the most common applications is rectification or diode are used as a rectifier. So what are basically rectifiers? So rectifiers are the devices which convert AC to DC, that is alternating current to direct current. So silicon and germanium are the most common example of the diode, and here we are talking about the silicon as diode. So silicon is the most commonly used material which is being used as rectifiers. So the basic principle, if we talk about a rectifier, it's basically uh, is the operation of rectifier diode. It's its inherent ability to allow current to flow only in one direction. Because of that particular property, it's being used in rectification. When AC voltage is applied across a rectifier diode, only half of the AC waveform, either positive or negative, is allowed to pass, while the other half is blocked. So this converts the AC waveform into pulsating DC waveform. This is the application of a diode. As we can see here, this is a semiconductor, and this is a complete rectifier. So this is a half rectifier. So if we apply a complete wave here, so if we apply a wave here, it is something like this. So this is a wave. If we apply this wave here, so at the output of this rectifier, we only get this half wave. That's why it's known as a half wave rectifier, because here we have used only one diode as being represented as D1, and diode, as we have already discussed, it has the ability to conduct current in one direction and block the other directions, as a result of which only half of the wave is being received at the output. So it is its application is not application is the characteristics of half wave rectifier is it uses a single diode. Only one half of the AC input wave, either be positive or negative, is passed to the output, while the other half is blocked. And because of this half rectification, its efficiency is not as good as the full wave rectifier that we are going to discuss in our next topic. So if we talk about the half wave rectifier, basically what happens in half wave rectification, the rectifier conducts current only during the positive half cycles of the input when the AC is being applied. The negative half cycles of the AC supply are suppressed during the negative half cycle. No current is being conducted, and hence no voltage appears across the load. Therefore, the current always flows in one direction through the load, though every half cycle, after every half cycle. So we can see the circuit details here. So if we see this figure, and if we see that if we apply the this wave, the complete wave is being applied here. So this is being shown here. Basically what happens, uh, the AC supply which is to be rectified is applied in series with the diode, and here at the output we have a load resistance. So a load resistance is being connected here. So if the output is being received across this load resistance, so this is basically a complete circuit. Uh, and AC supply is given through a transformer. So initially we have a transformer as being shown here in the full wave rectifier. We have a transformer here. The purpose of the transformer basically has it permits two advantages. Firstly, it allows us to step up or step down the AC input voltage as the situation demands. Secondly, the transformer isolates the rectifier circuit from the power line and thus reduce the risk of electric shock. So it always passes through the transformer. So how does it work? AC voltage across the secondary winding, if we see there if we have applied an input here, and then here we'll be having the transformer winding, primary transformer and the secondary transformer. AC voltage across the secondary winding, it basically changes the polarity after every half cycle. During the positive half cycle of input AC voltage, so when we have applied this positive half, this half of the complete input, uh, so what will happen, this particular end on which the positive half is being applied, it becomes positive and with respect to the negative half. This makes the diode forward biased and hence it conducts current. During the negative half of the cycle, when we have applied this, so this end will become negative and this end will become positive. So the reverse will happen. So under this condition, the diode will be reverse biased, because here when this end becomes positive, so diode is also there, which is p type. So this diode is connected to the positive half of the cycle, so, with the positive end, as a result of which positive is connected to the p side. It means during the positive half cycle it will be forward biased. But when we apply the negative side, so this end will be negative, this end will be positive. It means negative side is connected to the positive side, or to the p type of the diode, as a result of which this will be a reverse bias. So as a result of which, when we see the output across the load, we only get the half of the input wave, because our diode, the one being shown here, which is only one diode, it conducts only in one direction when it is forward biased. So during the negative half cycle, no current will be there, no conduction will be there, as a result of which we won't get anything in the negative half, for the negative half of the cycle. Again, when the positive half is being applied again, so we will again getting the output corresponding to the positive half of the cycle. This is how it works. Because of that, because we are not completely getting the output, as a result of which this is less efficient, since the half of the input power is lost here. Talking about the full wave rectifier, how it is different from the half wave rectifier, because in full wave rectification, instead of one diode, we use two diodes, as being shown here in the figure. So we have the two diode, and this type of arrangement where we have load resistance in between these two diodes, it is known as the center tapped full wave rectifier, because it being centrally tapped here, it's being shown here. So this is a transformer, the primary transformer and the secondary transformer. So this particular diode, this particular rectifier, it works with the two diodes, which is different from the half wave rectifier. If here we use this only one diode, and that's why it gives us only half of the wave. But here we uses the two diodes. So full wave rectification, here the current flows through the load in the same direction for both half cycle of the input AC voltage. So this can be achieved with the help of the two diodes working alternatively. So at one point will be one diode working, at another way you'll be having the other diode working. For the positive half cycle of the input voltage, one diode supplies current to the load, and for the negative half cycle, the other diode does so. The current being always in the same direction through the load. Therefore, a full wave rectifier utilizes both half cycle of input AC voltage to produce the DC output. So mainly this configuration that I have shown here is a center tap full wave rectifier. So this circuit employs the two diodes, diode D1 and D2, and a center tapped secondary winding is being used here with the two diodes connected, so that each uses one half cycle of the input AC voltage. In other words, D1 utilizes the AC voltage appearing across the upper half. So this is the upper half of the secondary winding for rectification, while the diode D2 uses the lower half secondary winding. So if we how does this full wave rectifier works? So if we apply a cycle here, we apply the AC wave. So during the positive half cycle of this particular wave, this end of the secondary winding, it becomes positive, and this end becomes negative. So when this is positive, so this is the P side of the diode, as a result of which, when this side is positive and this is diode, this is the p side of the diode, so it means positive is connected with the positive. So diode D1 will be conducting at that particular side, and this side will be negative. It means negative of this side is connected to the p side, so it won't be it won't be conducting. So this diode is working during this positive half of the cycle. Now when we apply the negative half of this particular cycle, so this winding will corresponding to the negative, and so this will be this secondary winding will be negative. So negative is connected to the positive side of the diode, and this will be positive. So positive is connected to the positive side of the diode. It means for the negative half of the cycle, diode D2 will conduct, but diode D1 will not be conducting. So as a result of which, for the negative half cycle, D2 will be conducting. So at the output, we will be getting such kind of output. So it will be something like this. For the positive half cycle, this will be conducting. For the negative half cycle, this will be conducting. Again, for the positive half cycle will be this. Again, for the other cycle, we will be having this. So this is how your conduction will take place. So in comparison to the half wave rectifier, we don't have anything in between the positive half of the and the negative half. But here, because we have two diodes, so at one time one diode will be conducting, at the other cycle the other diode will be conducting. So as a result of which, this diode is more efficient in comparison to the half wave rectifier, and it has more efficiency, and the amount of ripples are also being lesser here if we see the comparison of the full wave rectification with that of the half wave rectification. Similarly, so we may say that diode D1 is conducting at this particular point, the D2 will be conducting this for this, then again D1, then again D2, and this cycle will go on like that. So if we see the advantages and disadvantages of half wave and full wave rectifier, so the disadvantage of half wave rectifier is that the pulsating current in the load contains alternating component whose basic frequency is equal to the supply frequency, as a result of which filtering is required to produce steady state current. So in order to have the steady state current, we have to use filters so that we can get the stable current conduction during the half wave rectifier. And the AC supply delivers power only half the time, therefore the output is low in case of the half wave rectifier. And if we talk about the full wave rectifier, although its efficiency is better than the half wave rectifier, but it has also its own disadvantages. One is it is difficult to locate the center tap on the secondary winding, and the diodes used must have high peak inverse voltage. So what is peak inverse voltage basically? The peak inverse voltage is suppose if we have Vm is the maximum voltage across this half secondary winding. So we have here, we have the, for half secondary winding, for this particular winding, we have the value of Vm, which is very high, or maximum voltage. So so instant secondary voltage reaches its maximum value in the positive direction. So at this instant, diode D1 is conducting. At this particular point, we will be having diode D1 is conducting and this particular diode is non-conducting. Therefore, whole of the secondary voltage appears across the non-conducting diode. Consequently, the peak inverse voltage is twice the maximum voltage across the half secondary winding. So that's why that is known as the peak inverse voltage, which comes across the non-conducting diode. If we are talking about the diode D1 having voltage Vm, so for the other non-conducting diode, the peak inverse voltage will be equal to 2 Vm. So diode must will have the high peak inverse voltage in case of in the full wave rectifier. So it becomes a disadvantage for that particular rectifier. So then we have the Bridge rectifier. So bridge rectifier is also the part of the full wave rectifier. In the bridge rectifier is the arrangement of the four diodes, which is being shown in the bridge formation. So we have diode D1, we have diode D2, we have diode D3, and we have diode D4. So the combination of all these diodes combine to form a rectifier, which is known as the bridge rectifier, and it provides the same polarity of the output for either polarity of the input. It is widely used for converting alternating current from a power supply into direct current. So how does it work? For the positive half of the cycle, during the positive half of the cycle of the AC input, the upper end of the transformer secondary winding becomes positive, similarly and as we have studied in the center tapped full wave rectifier, and the lower end becomes negative. And at one time we'll be having two diodes conducting. For example, for the positive half of the cycle we'll be having D1 and D3 conducting, and for the other two cycle will be having D2 and D4 conducting. So the current flows through D1, enters the load, and this return back flowing through the D2. For the negative half of the cycle, during negative half of the cycle, the other two, for example, we have applied the negative polarity, the upper end will become negative and the lower end becomes positive. So this forward biases diode D2 and D4, and diode D1 and D3 will be negatively biased. So, or it will be reverse biased. So in both half cycles, the current flows through the load in the same direction, resulting in the pulsating DC output. So this is how your bridge rectifier takes place, bridge rectification takes place. So this is also the part of the full wave rectifier. And however, it has advantages that the need for center tap transformer is eliminated if we have the bridge rectifier, and its output is also twice in comparison to the center tap rectifier. But it has also disadvantages because we need four diodes at a time, and so this is also one of the disadvantages of the bridge wave rectifier. So next we have how we calculate the in case of, because we are studying the rectification, so in case of rectification, few characteristics of the rectifications are very important. First of all, the ripple factor. So what is a ripple factor? So ripple factors are ripple factor is basically it consists of the DC component and AC component. Because if we talk about a rectifier, it converts AC into DC. So at the output, you should be having the DC. But apart from DC, we have some part of AC at the in the output. So that particular AC component is known as the ripple. So AC component is undesirable, that we don't want. So and accounts for the pulsation in the rectifier output. So the effectiveness of a rectifier depends upon the magnitude of the AC component in the output. The smaller this component, the more effective is the rectifier. So the ratio of the RMS value of the AC component to the DC component. So we may see here the RMS value of the AC component to that of the value of the DC component. It's basically give the ripple factor. So ripple factor is very important in deciding the effectiveness of a rectifier. The smaller the ripple factor, the lesser is the effective AC component, and hence more effective is the rectifier. So ripple factor has to be small if we want if we want our rectifier to be more efficient. And as you have already understand that this is the AC component in the output DC, so we need to avoid that AC component or the pulsating output, so that our rectifier may have the better efficiency and it may work better. So half wave and full wave rectifier has different value of the ripple factor. For half wave rectifier, that value is 1.21, and for full wave rectifier that value is 0.48. It means for half wave rectifier, the pulses or the pulsating component is higher in comparison to the full wave rectifier, which has ripple factor 0.48. So the ripple factor has to be low in order to have a rectifier to be working efficiently. Second, we have the rectification efficiency. So rectification efficiency is the ratio of the output DC power to the input AC power. It gives a measure of how efficiently the rectifier converts AC power to DC power. So for a full wave bridge rectifier, it is given as, so this is the efficiency, is the ratio of the DC power to the load and which is being divided by AC power from the transformer. So if we take their ratio, we'll get the rectification efficiency. So the efficiency of the full wave rectifier is better than that of the half wave rectifier, and for a ripple for a rectifier to have better working, its efficiency has to be higher in that particular rectification. So for so in this particular module, we have studied about the characteristics of a diode, what is PN junction diode, and what are the VI characteristics, what is their application. So first part of the application, in the first part of the application, we have studied about the rectifiers, the half wave rectifier, full wave rectifiers, and how do they work, and which is better, and how their working ability depends upon various factors like ripple factor and the efficiency. In our next part of this module, we are going to study about the application as LED and solar cell and photodiode. So after this completion of the module, I will provide you with the quiz. You have to solve that quiz, and if you have any queries regarding this particular module, you may email me, or we can create a link so that we can discuss our queries about this particular module. So with this, I would like to thank you, and please go through this module.